My guest today is Priyanca Ford, who is the founder and exec board member of Kronos Fusion Energy. Priyanka has dedicated her career to developing algorithms and machine learning simulations for fusion energy generators. Welcome, Priyanka.
Hey, Gil, good to be here. Thanks for having me.
Yeah, thanks for doing this. So, fusion energy has been in the news. I just saw a paper from Princeton. It just came out a couple of days ago. But before we get the details of this, what exactly is fusion?
Fusion is a nuclear reaction where you fuse lighter elements to create a heavier element. And the
Lighter elements
process,
to create heavier elements. So we could actually go down the periodic table and till some point, I suspect it's lead or something like that. We could take some even heavy elements like carbon or something like that, fuse them together, get to a heavier element, and it will release some energy. So there's a whole spectrum of things there, right?
right, definitely. So with fusion, we're mostly talking about hydrogen isotopes. So this is deuterium, tritium, and helium-3. And you could do, there are like two others you can do, but for the most part, most of the research for the last 50 to 60 years of fusion energy has been around deuterium and tritium. So it's hydrogen isotopes. And when you fuse them, you get either you get neutrons and you get an helium-4,
Yeah.
which is dissolvable, soluble in water, and it's absolutely not radioactive. So depending on your fuel composition, you either get neutrons or you don't get neutrons. And I think different companies and different research facilities have chosen to do some permutation and combination of those fuels.
So is there a reason we prefer deuterium and tritium? Is the sun burning ordinary hydrogen or deuterium?
So the reason we have so far the industry so far uses deuterium and tritium is because it's easier to fuse. So the two tried and true ways that so maybe we should talk a little bit about the main types of fusion energy confinement.
Yeah.
So there's inertial confinement and then there is magnetic confinement. So fusion is pretty much um, the most prevalent process in the universe, in that stars are made up of fusion energy. And so stars are mostly magnetic fusion, and the magnet part of this is gravity. So it's the gravity that fuses helium isotopes. And what you see when you look at the sun is you're looking at plasma. So this is plasma is a state of matter, is the fourth state of matter. We learned about 3 when we were in high school, and my daughter learns about 4, by the way. So it's the fourth state of matter where when you have ice, you have water, and then you have steam. And then when you keep heating steam to 10,000 degrees, you have plasma. So plasma is that state of matter. So the sun basically works with, there is a strong gravitational force that is fusing hydrogen isotopes, and it's creating this plasma that has heat. Now, what we want to do is we want to create a small version of that, but we want to harness the heat and then turn that heat into usable energy for uh, yeah, there we go. We want to harness that heat. And so with deuterium and tritium, you need less of that gravitational force. So you need less of a magnetic force to fuse deuterium and tritium. But when you fuse deuterium and tritium, you do have a neutron that comes out of this process. Now, there are two issues with that. It's hard to harness the neutron, and you kind of still run into the neutron problem in fission energy, which is harnessing the neutrons. However, with fusion, there is a way to have that neutron interact with the wall of the reactor, where you need to put a lithium coating on the wall of the reactor. And when that neutron interacts with that lithium, you then get tritium, which allows you to have a self-sustained process. Not a completely, but it adds to the fuel that you need in it. Now, over the last 60 years of fusion energy, about 80%, and this is an arbitrary number, I'm just kind of throwing out so a large percent, about 80% of the research has been with magnetic confinement fusion. So this is tokamaks that have a very strong magnet that keeps a plasma intact because of the strength of the magnet, and you fuse hydrogen isotopes in that plasma field. So that's pretty much magnetic confinement. Inertial confinement is you have a set of lasers that then target a fuel cell, and this looks like a pebble, like a BB gun, like one of those things, like a BB. And you target that with, and this was a breakthrough in Lawrence Livermore National Lab.
I saw that, yeah.
At the National Ignition Facility. And so they target this, and they target a BB that has deuterium and tritium in a sub-zero sort of very, very cold state. And then that, that rapid heating of that then releases energy, and then that's the inertial confinement fusion. So they're the two types of attaining fusion. And there are others. There's like linear fusion, which uses some aspect of both of those. There's also there are a few others. There's something called field reverse configuration, which if it works out, it would be amazing for space travel. So fingers crossed for that one. So different companies are trying to achieve fusion in different ways, different fuel compositions, and different temperatures, shall we say?
Yeah.
Yeah.
So this is a race. If whoever finds the right combination, I know Germany, France, Japan, United States, I don't know what China's doing, UK is doing some interesting things. Everybody is trying to get to the finishing line here.
Yeah.
So I want to talk a bit about the company that you founded, Kronos Fusion Energy. So what is sort of your methodology and concept and technology? Where are you heading with it?
I solely started this from a mathematical perspective. That's my background. So I used to write. I was involved in a lot of automation and writing algorithms. So I got into fusion energy algorithms when I did a project for an energy company a while ago. Long story short, we really didn't think we were going to do anything with it or start a company with this. What we wanted to do was we wanted to harness the latest sort of computing prowess in Silicon Valley, and there were about 5 of us that banded together, and we started building simulations. So it was kind of bootstrapped, we were self-funded, and this is what we did. So for the better part of 6 years, we worked on perfecting our plasma field. We looked at all of the various designs on the market. We looked at all the research that's been published since like 1950s, and we found we had a goal. We wanted to commercialize fusion at a levelized cost of energy of 40 cents per kilowatt hour, because we felt that if we could do this, then that would be the measure of commercial viability for like large scale commercial. We're talking 100 generators. So if we were going to build in that scale. we needed to reach that point. So
Let
we
me
thought,
let me ask a quick question on that, Priyanka.
yeah.
So, if I understand this correctly, there is a huge capital cost.
Mhm.
There is, huge investment needed up front. But if you get a sustainable fusion um, process, then the operating costs are not, assuming that everything goes well, the operating costs are not very high, right? So when you say 40 cents per kilowatt hour, it is sort of a depreciation of the equipment you're thinking about, or is it's a really operating cost?
It takes both into account. So the actual equation for it is, like your total cost versus your output, right? So your cost has the depreciation built into it, the LCOE equation does. But what it really also signifies is like a maturity of the technology in and out
Hmm.
of itself, because you're kind of assuming that your research costs are not as high as they are or were in the fusion energy industry for the last 40 years. So we're kind of standing on the shoulders of giants, really. Like there's no way we could have touted that number about had it not been for ITER and some of the Eurofusion efforts that you mentioned. I think JET was a big part of it, and we yeah. So I think we have just come into the marketplace like at a time where we can say that such a thing is achievable because all of the physics research has been done. What we need to really worry about is the engineering part of it, which is what we're working on now. So we don't have to spend billions of dollars building a prototype to prove out whether or not the plasma works. What we can do is use an AI and look at existing plasma research and say, what kind of measurements do we need? What kind of elongation, radius of the plasma? So there's a lot of existing things that we have leveraged on and used, basically algorithms to automate a lot of it. We've tried to leverage machine learning to optimize a magnet output. And so there's a way that we are targeting this levelized cost of energy by not only optimizing the fusion energy aspect of it, but also the whole energy generation business of it, the production, the transmission, the putting it into the power lines, putting it into your grid, and
Yeah.
actually powering the house. And that whole process can be automated if you throw a lot of money and computing at it, I suppose. And then there's also and there's also like the supply chain factor, right? Like if you're going to have something that produces a lot of neutrons, if your fuel composition is such that you produce a lot of neutrons, then your material costs are going to be higher. The materials you need to harness this thing is going to be a lot more expensive. And that adds to your operational costs. It also adds to your downtimes, and your downtimes eventually add to your cost as well.
Sorry. Yeah.
No worries. So I think like it's all of those together, and I think that there's a part of me that's also betting on the success of other fusion energy efforts, like magnet efforts that are out there in the world. I want to see the European efforts be successful, because I think that all of that adds to achieving that levelized cost of energy.
Yeah.
Because at the end of the day, it's not going to be the design that's best that becomes that large commercial design. It's the design that can do it at the right cost and can make it accessible as a product.
Yeah. So I want to understand this a little bit, Priyanka. So there are multiple, as you say, multiple engineering complications here. One is we have to hold a plasma that is potentially tens of thousands of degrees of temperature Kelvin. And we don't have materials that'll hold it. So you have to hold it sort of in space, in space time, so to speak. And so we could We could use magnets for it. We could use other aspects for it. But at the end of the day, as you say, there are multiple efficiency problems here. So there's an engineering efficiency question. So, we got to heat this thing up for a period of time that takes a lot of energy. You have to sort of get the energy out and create electricity from it. There's sort of inefficiencies there too. So there's a fusion efficiency, there's an engineering efficiency, there's a conversion efficiency. You put it all together. The question is, are we going to get more than we put into it, right? That is the fundamental question.
Yes, I think the physics supports it. The fundamentally, I think it's there. But yeah, it's definitely not devoid of challenges. We do have a long way to go. I am skeptical of any timeline that's shorter than 5 to 6 years, because I feel like if you're going to achieve, it's not even just achieving fusion, it's achieving it at a steady state that is then sustainable and practical for commercial use. So I think we're a decent 10 to 12 years away till we can achieve a generator at a steady state and that it's plugged into the marketplace and can reach that levelized cost of energy. Yeah. But I have hope. We saw research out of University of Houston where the HTS tape, the Rebco tape that's used to make a high temperature superconducting magnet that can harness the plasma. It used to be about 40% of the cost of the generator. Up until now, it's kind of scaled that way for the last few decades. And now there's a team of people. Never underestimate what a small group of people can do, right? So there's a small group of people out in Houston, and they have a superconducting tape that's 30 times stronger at 10% the price. And so this dropped our cost of superconducting. We need about 35,000 meters of this tape in order to achieve what we're trying to do with our generator.
Yep.
And the cost of our tape went down from $1.2 billion to about 160 million. So and this happened over the course of the last year. I mean, that really helped my COE there, right? And you're right. They're like the plasma heating. So there's the ignition and you have to sustain the heat, and you got to get it up to that temperature. So, but there are startups that are spinning off out of Lawrence Livermore National Laboratory, like the ignition facility, where they're actually building ignition systems for inertial confinement that could potentially be used for magnetic confinement units. So, the best minds are figuring out like the smaller problems, and we have a partnership where we've spoken to a fission energy company who tells us that they can harness the heat out of our fusion energy generator, and they could potentially build that unit for us. And this is something that they can leverage existing technology from the fission world, and it's something that we can use. And so
for electricity generation, for power generation.
Well, it's for industrial heat harnessing.
Okay.
You could always harness the heat and run it through a steam power plant and generate electricity.
Yeah.
But this is for like liquid fuel manufacturing, steel, cement. I think steel, you need about 1,700 degrees to process steel, and it's about 17% of your carbon emissions in your atmosphere. So, if we can do, even before we generate electricity, we feel like we can create an industrial heating unit. Especially for those high temperature things like the cement, the steel. I want to incinerate garbage. I don't know what temperature we need to reach in order to burn garbage, but I've spoken to companies that can burn waste and create carbon fiber with it, which we can then use in our generator to actually harness any of that heat. So we have some cyclical partnerships we're working with. But you're right. It's incredibly complicated, and that's the best part of it. That's what makes it fun.
Yeah.
And it's not done in a silo. You got to play with other kids.
Yeah, I mean, it's almost like fundamental innovation. We have some ideas. We know it works because we can see the thing rising in the east every day. uh, and it seems very stable and very useful. And so we know fundamentally it works, but the question is sort of an engineering question, which is, can you get sufficiently productive, efficient process going that's sustainable? And unlike nuclear fission, the beauty here is that if it doesn't work, it shuts down. So there is not, sort of the fission related problems that we've been trying to handle in nuclear power plants. But yeah, so can we sustain it? I know that Germany has a different design. Japan has a different design. So a lot of different designs sort of floating around, right? So, Priyanka, as I was mentioning, when I got out of engineering school in the 80s, I thought there would be two problems that would be already solved by 2000. One of them is nuclear fusion, and the other is room temperature superconductivity. And I was just looking at all the material science innovations that were happening in the 80s. I thought, yeah, these are easy problems. In 2024, we haven't solved either. And so, what do you think? Are we heading in the right direction?
Oh God, yes, definitely so. I'm very, very optimistic for this. I feel like there are different designs, and we have enough, and by we I mean the fusion energy community as a whole, or humanity as a whole. We have enough to prove that there are about 3 or 4 different ways of achieving fusion that work for sure. That
Yeah.
work for So Germany has a stellator. That's what they work on. That's the Wendelstein. And so they're building a new version of it, and there are stellator startups in Germany that are spun out of that project. And the Max Planck Institute is an exceptionally great place for engineering, and they've built this thing. It works. We know that we can achieve fusion, but stellators are incredibly expensive to make. We can make 2 tokamaks and achieve the same energy output as a stellator. We could still save a little bit of money there. But it's worth exploring because it has specific uses where it fits in very well. One, it doesn't have it works more on the magnets and a little less reliant on the plasma itself, which makes it great for perhaps space exploration where you don't have to keep it stable all the time. So it has its place. In terms of the big issue is the material issue now.
Yeah.
It is a material issue. I would say it's about 40% of the problem now. And we've thought about this. So the material issue really comes into place based on the fuel that you're using, right? So if you have a fuel you're using that produces a lot of neutrons, then you need a robust material that can harness that neutron as well as contain the heat. Those are the two things.
You need some sort of blanket type thing, like lead or something that sort of picks up all the neutrons.
Yeah, but it's not so. Yeah. No, it's a lithium. It's a lithium blend that picks up on the neutrons. But what do you then do if there's a crack in your system? Like what if the wall breaks? And so you still have. What if you have a leak of neutrons? Is really what I'm saying, right? Yeah. And so if you can you run that in a steady state? Like, can you run it for 4 hours and still harness the neutrons and have this process going? And simulation suggests we don't have a material that can do that yet. I
Okay.
am hopeful, however, because we have a lot of breakthroughs all the time, especially material. So it's possible. For our design at Kronos, we have an aneutronic fuel. So what we're trying to fuse is helium-3 with helium-3. What this does is you don't have any neutrons. You still need the materials to build the walls and harness the heat, which is doable. But we don't have any neutrons. However, we come with our own.
Sorry, Priyanka. So you said you're fusing helium-3. So you're fusing helium-3. So what's the end product then when helium-3 gets fused?
You get helium-4 and
Helium-4.
proton. And so that proton then allows you to convert it to ions and harness electricity through direct energy conversion as well. So you get that. So, but it's incredibly difficult to do. It's about 4 times more difficult to fuse helium-3 than it is to fuse deuterium and tritium, just for. However, if you manage to build a magnet that's strong, which is what we're doing, we're building a magnet that's strong enough that can have a plasma that's strong enough, and we're trying to fuse helium-3. However, if you manage to solve that problem, you then are less reliant on the material issue for commercialization, because now you don't need to have this material that can do the heavy lifting when it comes to harnessing the neutrons. It still has to be able to contain the heat, and the more and if we could have some breakthroughs in superconductivity, your other hope for the turn of our century, that would also help with the direct energy conversion in an aneutronic device. But like the aneutronic device, you need a stronger magnet to do it. So just for a little bit of high level scale, in order to fuse deuterium and tritium, you need a 15 to 20 Tesla magnet to accomplish that. In order to fuse helium-3, you need to have at least a 35 Tesla magnet, which is what we're shooting for. And in order to achieve that magnet, you need breakthroughs in that Rebco tape technology, which is why we're excited about the Texas folks.
Will you get into? Sorry, will you get into some sort of raw material problem here? So helium is not readily available, right? Helium-3.
Helium-3, it's not readily available. It's there are 3 companies that we know of that are going to the moon in order to fetch helium-3.
Oh, okay.
I'm also told that the moon has some sort of specific soil that acts as a super fertilizer. So the motivation for a lot of space programs going to the moon is the helium-3 and the fertilizer. This is what so we're kind of hopeful, the fact that we don't have neutrons allows us to also build a modular generator, and we feel like that's has space applications. Since it's modular, we can have robots assemble maybe 15 to 20 parts in orbit, and then we're closer to the moon. So fingers crossed. Yeah.
And no radioactive issues. So yeah, I'm quite interested in sort of a neutronic, as you say, process. I mean, the problem with fission is that we have waste that we have to take care of for 50,000 years, which is typically not considered into the cost equation. So when people go out and say, "Oh, nuclear energy fission is so beautiful," it's not quite that beautiful, is it?
It's not. Yeah. It's not. It's tens of thousands of years. Like it's sad. Um, I used to work at Edison International that owns a nuclear power plant out here in Southern California, the San Onofre nuclear power plant. And I was there at work the day that Fukushima happened. And I was like, do I drive in? Like, what do I do? Like, um, so I went into work and my God, the panic, uh, the fear, everything that we went through that day. I mean, this plant has been shut down now for the better part of, I want to say, a decade. But yeah, you never have to worry about that with fusion. That's a huge plus. But if you are going to then have a generator that has neutrons and a lithium wall and it's producing tritium, and you have connected a tritium recovery unit or something like that to it, which would be compulsory for a unit like that. This is something that you would need to build.
Yeah.
You are then getting back into the weaponizable territory, right? But it kind of defeats the purpose. So one can only hope that the deuterium tritium is a step towards ultimately an aneutronic helium 3, because now you have a truly non-weaponizable system with an available supply chain, but you have to have a better ignition system, a better heating system, and you need to have a stronger magnet, which I feel as a as there are so many research projects out there that are so aware that solving these issues solves fusion, and they're working on it. So I'm very hopeful. I feel like we're going to have at least 5 or 6 other gigantic breakthroughs over the next decade.
I hope so too. We need it. So I want to talk a bit about your machine learning algorithmic work. As I mentioned, there's a Princeton paper that just came out, and they claim they have used reinforcement learning to come up with a really good way to hold the plasma. But it's specific to a one technology or one instance of the technology. So I don't know if it's truly generalizable. But this is something that you have done a lot of work in, right?
Mm-hmm. Yeah, we've for me, it's been majority of my work, and then I brought in other partners who are experts in other things. So yeah, I mean, Princeton Plasma Labs is amazing. Just amazing group of folks. What they do is spectacular. Most of their computing is done at Oak Ridge National Lab. So I think Oak Ridge has the most fusion energy calculations ever done is stored in Oak Ridge. And uh, I know that there are a lot of efforts towards using quantum computing for fusion now as well. So I think there are more breakthroughs to come. But I think what Princeton Plasma Labs was talking about is plasma dynamics. So it's
Yeah.
actually containing the plasma and applying AI and machine learning to that effort, which really makes sense. Because see, the thing is, we have all this stored data from these databases from decades and decades and decades of research. Um, the greatest scientists went after fusion before they went after fission, because the goal with fusion has always been this sort of abundance and world peace and that kind of state of mind.
Yes, yes.
And fission has been like, let's bomb them, and there's a lack, and like, how do we leverage this? So, I mean, I'm sure like people saw the Oppenheimer movie. That dude was super depressed about being diverted from his fusion work and like putting and being pulled towards fission. But so we have all this research and there's all this data, and we have all these codes that have been developed in different national labs, Los Alamos, Livermore, Oak Ridge, PBPL. Those are the main ones. And University of Wisconsin has done some heavy lifting with plasma research as well, especially with helium-3 aneutronic fusion. They have 4 different prototypes that they built just to test this. So,
Hmm.
yeah, so, there was a way to put all that data together and throw a supercomputer at it because the logic existed and the codes existed. We just needed to turn the logic into algorithms that you could feed into a supercomputer and get some sort of results that helped you optimize better. And now
Yeah.
with AI and what we can do in terms of automating development, automating code development using AI, we can almost do that at a hyper scale, right? And then we do reach a point where we want to figure out exactly what dimensions, whether it is the shape of your generator, the elongation of it. You would need to put all of those variables together, and then you have like this controlled plasma field.
Yeah.
And plasma dynamics also has a very big component called mitigation algorithms. And I spent about 2 years on this stuff. So mitigation algorithms is basically in the instance where your plasma field is not contained, because what you have are these sort of instabilities that happen with your plasma field that throw off your system. When you have those instabilities, how can you use algorithms and AI in order to control it as fast as possible so
Hmm.
you don't create huge amounts of damage to your generator wall? So there are mitigation algorithms that go into plasma dynamics that are just so beautiful. I mean, this is I could talk about this all day. Tell me when to
So
stop.
do you call it sort of the tearing instability? So the plasma is in there, and I'm thinking about my engineering days about fluid dynamics. I don't know if plasma actually behaves to conventional fluid dynamics um, process, does it?
Um, I don't know. Uh,
Yeah, I mean it's really interesting. I mean, this is truly the engineering problem to solve, which is can you hold a mini sun um, optimally, right? So your work and others, there are two things here. One is sort of predicting things are going downhill as early as possible,
right.
and then the other is the mitigation. Given that prediction, how do you mitigate it? Because the goal here is to hold that plasma as long as possible, right? Without getting out of it. Yeah.
Yeah, and really a lot of that credit goes to the breakthroughs with the high temperature superconducting magnets. It is that so it that was the breakthrough at MIT about 2.5 years ago. So MIT has a startup, well, not a startup anymore, a fusion energy company that spun out called Commonwealth Fusion Systems, and
Yeah.
so had the breakthrough, and they've done amazing work with basically creating a magnet system that can harness a plasma. And so the lead for that magnet, the lead of that magnet design, his name is Carl Wegel. He's my founding partner at Kronos. Because we need we need that 35 Tesla magnet. So he's the one that designed our magnet as well. But that breakthrough, it was really something. Like, it was that breakthrough that kind of made a lot of people in the fusion energy world recognize that, hey, a private company can do this. Like, this is
Mm.
not in the lab anymore, right? And so that plasma, we were never really able to achieve the stability in the plasma before that high temperature superconducting magnet. And it also comes down to the Repco tape. This tape is like uh, it's micrometers thick, but it's built with 7 different layers of superconducting material that
Mm.
make it like this really strong superconductor that is then wrapped around coils to basically then you place all of those magnets, those colloidal field coils and toroidal field coils, you then place them in a way where you have a flowing electromagnet system. And and the stronger you can make that system, the better you can stabilize your plasma. And that's really what that breakthrough achieved. So a combination of the AI along with the magnet, those two things have helped really stabilize the plasma. And the fact that I can even sit here and say that, hey, I'm gonna fuse helium-3, that would have been impossible without that superconducting tape. That's absolutely impossible. But because of this, we can now create these really large, really strong magnets. It's possible. I don't know what to say.
Absolutely. You have to keep going at it. So it's sort of interesting. It is at the intersection of three major innovations that we thought were going to happen. Fusion, room temperature superconductivity, and quantum computing. It's at the intersection of all three of this. It's almost like you have to get all three of this to go to the next level. And we have to go to the next level, right? So we have to keep trying to put the puzzle pieces together.
Yes, yes.
And so I know that you built some sort of a simulator, right? There's some experimentation going on. Where's that?
I mean, it's a simulator that we basically house in our company, that we have about 24 partners that we built it. And I don't know, it's just something that we build and we use to perfect our technologies. What we're hoping we can provide it to a larger marketplace in about 2 to 3 years. What we're hoping to do is perfect our algorithm such that if you are a customer for us, so if you are a cement manufacturing company and you kind of tell us your goals and we can kind of feed in the size, the usage, we can feed in a few of your requirements into our simulator and have our algorithms then build like a simulator that gives you perfect measurements down to the nuts and bolts of things, like the size of your internal components, it needs to reach the temperature you need. So for a desalination plant, for example, it would be 200 degrees centigrade, right? But if you want to do something with biofuel, you're at about 700 degrees centigrade. And if you want to, we could also produce hydrogen. And basically, if you heat water up to 1,200 degrees centigrade, the hydrogen and the oxygen separates, and you can then harness the hydrogen. So we can produce hydrogen at about 1,200 degrees centigrade. So we have all these industrial uses and use cases. So what we're trying to do with our simulations is we should be able to have an interface where we plug in some of those variables and we should get a generator that is ready to be built. So prototypes like this used to cost at one point 2 billion, 3 billion in order to get the prototype. So we feel like we can build our prototypes from a simulation at this point.
But how does that compare with, let's say, concentrating solar? So I know Bill Gates invested in a concentrating solar plant somewhere in Utah or someplace like that. And so industrial applications of concentrating solar, I mean, everybody is after photovoltaic, and I always felt concentrating solar has a lot more potential. So, from a total capital cost and operating cost perspective, if you were to get an industrial application out of fusion, will that compete effectively with concentrating solar that we know how to do?
I think so. I think it depends on what you're trying to do. tell me this term again. What solar are we talking about?
So concentrating solar, basically not photovoltaic. It's basically just getting the sun's rays into a
Uh,
focus, and you can get a very high temperature by doing it properly. And so industrial applications like steel and other type of things, there has been. I don't know if there are anything. I mean, I know Bill Gates invested into one of these plants, but I don't know if it is really out there, actually doing it.
huh. I don't know that one. I just know that for a lot of solar technology that we see, I feel like it's better for home usage or residential use. We how I don't know how scalable concentrated solar would be compared to what we can do. And I mean, I was gonna say, what do you do at night? But then you're not doing your industrial work at night, so perhaps you don't need it at night. But you still have location limitations and seasonal limitations, and so and in terms of the energy you produce versus the waste that you producing that energy, I feel like in the long term, fusion is better because you could just produce more energy with what you build.
Yeah.
So I don't know.
Yeah, I mean, if we solve all these engineering problems, it's definitely more reliable. But as you say here, levelized cost of electricity is really what's going to drive comparisons between what we have and what we could have done or what we could do in the future. Um, but I always felt that fusion is a beautiful thing. We know it works fundamentally. We just haven't been able to do it from an engineering perspective. And engineering problems, as you know, it is something that we have always solved. So when a problem is reduced to engineering, we almost always solved it. And so I'm hopeful that we will do this at some point. So the timeline is what I want to ask you. What is sort of your gut feel about the timeline of some practical fusion excess energy coming out of coming out of a plant?
I think soon. I think Commonwealth Fusion will probably be the first to go. I think that they will. I think that they'll be successful in what they do. Helion Energy is a company that has that's announced that they are going to produce power to power a Microsoft supercomputing center, and they have targeted 2028. So there are companies that are that'll have these breakthroughs well before us. For us at Kronos, we aim to take our industrial heating unit to market in 8 years. So we have an extra 4 years ahead of them. So we're thinking about 8 years. We could have something at a steady state, something that is aneutronic and clean and modular. And the modularity also adds to lowering your operational costs. You could just take bits and replace them at a time, and costs and downtime. So we're hoping that we can build that perfect device and take it to market in 8 years. We do aim to have a fusion energy generation unit that will plug into the grid in about 12 years. So this would still harness existing steam generation. So we would have the heat and the water and the steam in the same way we do now. In about 20 years, we feel we could do the whole thing with direct energy conversion. So the big upside of solar is that you can stick a panel on your roof and you don't need to generate heat. You can surpass the heat cycle and you can have energy. We could do that with aneutronic fusion, and aneutronic fusion only allows for this direct energy conversion. And in about 20 years, we can build a direct energy conversion unit that can harness the protons and convert them to ions and then convert them directly into electricity. That'll take us about 20 years. If you want to look really ahead, once you have that neutronic system, you are now sort of signaling that you're ready to launch into space, because you can't send a whole steam generation unit out there. You can surpass that. So we feel like everything we're building is for the super long term, and I'm very California style laid back. So we have longer timelines compared to other companies. So I feel like when we announce, hey, here's our first one, there would be at least 4 or 5 companies that would have announced it before us.
Yeah. So are you still privately funded?
Yeah. Initially, I sold a 3D printing company in 2014, and I used every single dollar on my work up until about 2020, and then we had a venture capital that stepped in for our seed venture. So that's kind of where we are now. We're working with 12 different institutions globally to perfect our design, and once we do that, we'll have our simulations complete, and we'll be ready to build, and hopefully somebody will give us money to do that.
Absolutely, yeah. I mean, it's a great thing that you're doing. It's definitely a technology that we need to, in the grand scheme of things, to make the Earth more habitable in the grand scheme of things. So we definitely need this. That it is good that different experiments are being run by different countries. I don't know exactly what China is doing, but I know that, as I mentioned, UK, France, Germany, and Japan, and the US have things going on. So, yeah.
Yeah, no, sorry. We have ITER. ITER is a triumph of humanity. It's the largest human construction project ever fathomed, ever. I was reading an article the other day that said that during the Cold War, America and Russia, like, all negotiations had fallen apart. And they wanted to find one singular thing that they could still keep working on in order to have some sort of connection with each other, and chose fusion energy. So ITER was born out of this, and it's been an unbroken global relationship since then. And now I think it's 35 countries that are banded together in ITER. China, I read an article. China has had a couple of breakthroughs. They've had a fusion energy generator that they have built. One is an offshoot of ITER. They have had some announcements where they've said they're spending about $1 trillion over the next decade towards fusion energy in China. Japan has 2 startups that have spun out over the last year and a half, but they all have also had some breakthroughs, and they've been one of the original ITER countries. Europe, definitely. France is heavily into it. ITER is in the south of France, so that's big time. And lots of countries. I'm Indian, so India has been heavily into it. India has their own Plasma Research Institute, and they have a lot of research that they've done with ITER. In fact, I think about 40% of all of the components that went into ITER came from India, including the vacuum vessel, things like that. So it's a truly global effort. I think it's a testament to peace being a possibility.
It's sort of a moonshot, and so to get there, we need a lot of people to come together. And I was going to say, don't tell this to our greatest president. He might sell all of our intellectual property to somebody else. But so it needs a true, as you say, a true global configuration to come together. lot of different experiments, which is a very nice thing to see. Very, very different technologies, different results, and different ideas. So I'm pretty confident at some point we're going to figure this out properly. But as you say, it's potentially 10, 20 years out before it becomes sort of industrial size, practical application, right?
Yeah, I think so. I think so. But you know, it's an evolution, like every technology out there, and then there'll be that tipping point. And I think the tipping point will really be we need to have a couple of private fusion energy endeavors announce their
Yeah.
work. And even now, you know, you kind of see, you know, 5 years ago, I spoke at Harvard about using AI and quantum computing for fusion energy, and I had a back row of snickering human beings. There's no way. And now we have quantum computing projects at Princeton Plasma Labs has efforts that for they're trying to do. So it's all happening, and I think the culmination of various breakthroughs in a lot of different industries is really coming together. Fusion is ultimate science. I can't think of a single area of science, maybe not biology, but a single area of science that's not harnessed in making fusion happen. Like it's heavily mathematical, heavy on engineering, heavy on the physics. Truly the ultimate human dream.
It really is. I mean, it's puzzling that um, the process is very simple. We understood the physics maybe, I don't know, 100, years ago. Uh, and engineering has kept us behind, which is a very unusual thing, actually. Oftentimes, once we understand the physics or chemistry, engineering doesn't take that long to do it. This is one of those situations that, I often say, Priyanka, that God has a sense of humor. Whoever she is, she sort of teases you with these ideas, and then you try to get closer and closer. She pulls pulls the thing out of you. So this is one of those things. Just like in life sciences, we have similar things going on in life sciences. Actually, we understand the mechanism. We try to create a drug for it, and it sort of works, but then it stops working. We find other things. It's sort of a long, long process before
Right.
you get to something that is useful. Yeah.
Yeah, but there's a tried and true path of other technologies also doing this, and yeah, I don't know what to tell you. I I feel like having spoken to all the people I speak to in the fusion energy world, people that have been working on this for 40 years, 50 years at various labs, proving out things that these human beings were going into work every single day, never knowing that one day it's going to be commercial the way that that we talk about it today, and they dedicated their lives to it. Like our magnet designer has been designing magnets for the last 50 years, and he has been part of a multitude of projects, and I hear these stories from him. And what I hear is actually the engineers were all ready and willing. I keep hearing that funding ran out of all of these projects at very crucial times. And fission was prioritized because it was weaponizable, and it's just a reflection of the society we
It was
live.
easier. It was easier to do. Yeah.
Right, yeah, right. It was, and so I don't know. I feel I think that we have a way, and by we I mean humanity. I feel like we have a way of doing things in the last minute. We get that. And now we're at that moment where we gotta write this paper now. It's due tomorrow, and we're there.
Absolutely. Yeah. Yeah. Good luck with everything that you're doing, Priyanka. It's very, very important work. And I wish you every success. with it.
Of course. Thank you so much, Dick.
Yeah. So thanks for spending time with me. I really enjoyed it. Thank
Of
you.
course, me too.